This entire topic is about the first step of engineering, and it's honestly the most important one. It's based on the standard HS-ETS1-1. The big idea is simple. You cannot find a good solution until you have a crystal clear definition of the problem. Think of it like this. If you tell a builder, "Build me a house," they can't start. What kind of house? How many rooms? What's your budget? This first step in engineering is all about creating that blueprint. We're going to learn how to analyze a major challenge, like climate change, and define exactly what a good solution would look like. It's really important to know the difference between what a scientist does and what an engineer does, because they are two sides of the same coin. A scientist investigates the world to gain knowledge. They might ask, why does this specific bacteria make people sick? An engineer solves a problem using that knowledge. They'll take the scientist's answer and say, okay, now how do we design a water filter that removes that specific bacteria? Science is about the why, and engineering is about the how. This is the official standard, HS-ETS1-1 broken down. It's our roadmap. First, we'll analyze a major global challenge, like not enough clean water. Second, we'll specify criteria. That's just a fancy way of saying, how do we know if we win? Third, we'll specify constraints, which means what are the rules? And finally, we'll account for societal needs and wants, which is the human side of the equation. Will people actually use our solution? We're not just talking about any problem, like my phone battery is dead. The standard specifies major global challenges. These are the big ones. They're complex. They affect millions or even billions of people, and they're all tangled up with other problems. You can't solve a global challenge with just one clever invention. You usually need a whole system of solutions. New technology, new laws, and changes in human behavior, all working together. Here are some of the big boss problems that engineers are trying to solve right now. How do we make sure all 8 billion people on Earth have clean water? How do we stop our oceans from filling with plastic? How do we grow enough food for a population that's heading toward 10 billion? And the biggest one of all, how do we power our entire civilization without changing the climate? These are the challenges this standard is built for. Okay, so let's start. This is the detective phase. You must figure out the real problem, the root problem, not just the symptom you see on the surface. If you go to a village and everyone is sick, that's a symptom. A lazy engineer might just ship in a truck full of medicine, but a good engineer follows the trail. They'd find the problem is a contaminated well, but the root problem might be that the village has no easy way to test for bacteria or a process for purifying the water. Solving the root problem is the only way to create a lasting solution. Once you know the real problem, you have to define success. This is what criteria are. They are the goals, the grading rubric, the victory conditions. If you're designing a new water filter, you don't just say, I hope it works. You write down a list of what works means. For example, it must remove 99.9% of bacteria. If you test your new filter and it only removes 90%, you failed to meet your criteria, and you have to go back and refine your design. Criteria come in two flavors. The first is quantitative. This is anything you can measure with a number. Numbers are an engineer's best friend because they aren't ambiguous. For example, it must filter 10 liters of water per hour. That's clear. It must cost less than $20. That's a clear target. It must weigh less than 5 kilograms. You either hit these numbers or you don't. It's pass or fail. The second flavor of criteria is qualitative. These are based on qualities or descriptions. They're just as important as the numbers, but they're a little softer and more subjective. For our water filter, a qualitative criterion might be, it must be easy to use. Why is this important? Because if your filter requires a 20-step assembly process, nobody will use it, even if it hits all its quantitative numbers. Other examples are, it must be durable, or it must look safe, so people aren't afraid to use it. Now for the other side of the coin, constraints. If criteria are what you must do, constraints are what you cannot do. Constraints are the rules, the limitations, the box you are forced to design inside of. A lot of people think constraints are a bad thing, but engineers love them. Constraints are what spark creativity. Build a bridge is a boring problem. Build a bridge that can hold a train using only $100,000 and recycled steel. That's an interesting challenge. Constraints are everywhere in the real world. The most obvious one is cost. You almost never have an unlimited budget. Time is another. Your team has a deadline. Materials are a huge one. Maybe the best material for your water filter is super expensive, so you're constrained to using a cheaper, weaker plastic. And of course, the biggest constraint of all, the laws of physics. You can't design a solution that requires you to break the law of gravity. This is the last, and maybe most important, part of the standard. You have to account for society. You have to be a bit of a psychologist. An engineering solution can be 100% perfect on paper. It hits all the criteria and fits all the constraints. But if you give it to people and they hate it, or it's confusing, or it goes against their culture, it will fail. To understand this, we have to separate what people truly need from what they simply want. Needs are the non-negotiables. These are the must-haves for survival, health, and safety. When you're designing your water filter, the number one need is that the water is safe. It must remove the pathogens. If your solution fails to meet a need, it is a complete failure, full stop. Other needs include basic food, shelter, and safety from harm. Wants are different. These are the desires that make a solution more comfortable, convenient, or desirable. For our water filter, a need is that the water is safe. A want is that the water tastes good. This is a really important difference. The water could be 100% sterile, but if it tastes like plastic, people might be tempted to go back to drinking from the tasty but contaminated well. Sometimes you have to meet a want in order to make sure the need is met. Let's see how these all clash in a real example: a new car. As an engineer, you have to balance all these competing factors. The need is safety. It has to have working brakes and airbags. That's a legal and ethical must-have. The want is from the customer and the marketing department. It has to be fast. It has to look cool. It has to have Bluetooth. But then the constraint from the finance department is that the whole car has to cost less than $25,000 to build. Your job as the engineer is to make the trade-offs and find a balance that meets all these demands. Okay, let's run a full case study. Here's our major global challenge, scaled down to a city: reduce plastic bottle waste in our city's parks. This is a classic vague problem. An engineer can't do anything with that. We have to define it. Let's do our detective work. The symptom is plastic bottles in the trash. The root problem isn't that people are bad, it's that they get thirsty, and the easiest and most convenient option is to buy a disposable bottle. Our solution has to be more convenient than the problem. Let's define success. What are our criteria? First, quantitative. A successful solution must reduce the number of plastic bottles in park trash by 75% within 1 year. That's a clear, measurable goal. Second, qualitative. The new system must be more convenient for the average parkgoer than their current habit. This means we need to think about location. So let's add another quantitative one. Water stations must be within 100 meters of all major picnic areas. Now what's our box? What are our constraints? First, cost. The City Parks Department has given us a total budget of $50,000. That's it. We can't go over. Second, time. It has to be finished by May 30th. right before the busy summer season starts. Legal. The stations have to tap into the city's water lines, so they must meet all plumbing and health codes. Materials. They have to be vandal resistant. We can't just use standard plastic. Finally, let's analyze the needs and wants. The primary need is a public health one. People in the park need access to clean, safe drinking water. Our solution must provide that. But what about the wants? People want that water to be cold. This is a huge one. If the water from our station is 80 degrees, people will go right back to buying a cold bottle from a cooler. They also want it to be fast and look clean and modern. If our station looks rusty or gross, they won't use it, even if the water is perfectly safe. And we're done. Look at what we just did. We haven't sketched a single design or built a single thing, but we have a perfect one-page problem definition document. We took a vague challenge and specified the exact problem, the criteria for success, the constraints we have to work within, and the human factors that will determine if it works. This document is the blueprint. This is HS-ETS1-1, and this is the foundation for all good engineering.